Good morning, everyone. Today I'm going to talk about spin crossover in iron in lower mantle minerals, a wonderful topic in materials physics and fundamental in geophysics. This video motivates my research. What you're seeing here is convection in the Earth. Earth is a complex system, a dynamic system that has been evolved for 4.5 billion years. Difference in temperature between the interior and the surface drives heat flow by convection in the mantle. Hot material rises and decompresses, and there is partial melting that spills through plate boundaries and forming new crust with composition that we know very well. Also, it leaves behind a solid residue with different composition, which we will also see on the surface occasionally in some places. But what we don't have is a direct, considerable amount of direct sampling of the lower mantle that we would like to see. We have to rely on indirect information to understand the interior, the chemical composition, and the properties of the mantle. This process you are seeing here leaves behind a signature in seismic tomography, and seismic data, seismic tomographic images is what we rely on to interpret the mantle. This is the type of seismic tomographic maps that I'm referring to. This is a map of velocities, velocity amplitudes at 1500 kilometers depth. There are slow regions, and these are shear velocities. Slow regions correlate well with surface volcanism, therefore must be hot. Cold regions correlate well with subducting plates, corresponding to cold material subducting, but these regions should also have somewhat different chemical composition. They could have different chemical compositions, and this is what we try to understand. Use this information to understand the chemistry and the temperature of these different regions. This is the lower mantle, the region that I study, that in which the minerals undergo a spin crossover. Between 23 and 135 GPa, the temperature, the pressure varies between 23 and 35, temperature between 2000 and 4000 Kelvin. And these are the main phases of the lower mantle. Bridgmanite, magnesium silicate perovskite with ferrous and ferric iron and aluminum. Ferropericlase, solid solution of FeO and MgO in the rock salt structure. Dave Malwhite, calcium silicate perovskite. It's a minor phase. It doesn't change so much the properties of the mantle, so I'm going to discuss these two other phases here. There are news on this phase, but I'm not even going to touch that here. So, interestingly and importantly, X, the iron concentration in bridgmanite is about 10%, and in ferropericlase is probably smaller than 20%. So this is helpful in trying to understand in doing the calculations. So at each point in the Earth, we assume that the velocities are isotropic. In an isotropic medium, there are two elastic coefficients, bulk and shear moduli, and only two velocities, the compressional and the shear velocities, and they relate to this elastic moduli in this way. Rho is the density. So in order to interpret velocities in the lower mantle, that's what we have to calculate, bulk and shear moduli of different rock mineral aggregates at different pressures, temperature, and composition. So in 2003 and 4 is when the spin transition in iron in ferropericlase and bridgmanite were discovered. Iron at low pressure has a magnetic moment corresponding to approximately S, total spin S equal 2, and the low spin state has S equals 0. There is no magnetic moment. And this was discovered using X-ray emission spectroscopy. So this is what I'm going to tell you a little bit about spin crossovers. the thermodynamics of a spin crossover in ferropericlase, and what's going on with ferrous iron in bridgemanite, and then spin crossover in ferric iron in bridgemanite and ferric iron and aluminum. How does this phenomenon manifest in the lower metal? So the method is important. The FT plus U we have used from the very beginning, initially non self-consistently, but today self-consistently. Phonon for quasi-harmonic thermodynamics also computed the FT plus U, and we also used VIN2K, all-electron method, to compute Mohs-Bauer quadrupole splitting of this iron, types of iron. The spin transition or spin crossover. Iron, the 3D orbitals of iron in octahedral field, they split into a triplet, low energy triplet, and a higher energy doublet. The energy splitting is called the crystal field splitting. 6 electrons in ferrous iron, they enter, 5 electrons spin up and 1 electron spin down, and this is the energy configuration of electrons in this state. You have the crystal field splitting, and you have the Ohm's rule energy splitting, separating spin up orbitals and spin down orbitals. With increasing pressure, the crystal field splitting increases, but the Ohm's rule energy splitting or exchange splitting does not. So with increasing pressure, electrons start to move from high spin-up orbitals to spin-down orbitals. And you could have a configuration like this for up and 2 down, until at the highest pressure, the crystal field splitting is so large, you have all electrons in the spin-down state with S equals 0. High spin, S equal 1 is the intermediate spin, and S equals 0 is the low spin. The intermediate spin state is very high, has very high energy. It's a metastable state one can find, but has very high energy and does not play an important role here. So ferropericlase, you have iron replacing magnesium. High spin iron replacing magnesium, you have a deformation of the local octahedron like that. You have a Young-Teller distortion because you have the minority electron entering here in one of those triplet states, the T2G orbital, XY in this case. If you replace magnesium in the low spin state, iron, you have an octahedral contraction. That's the charge distribution in the low spin state. When you go from high spin to low spin, there is a huge volume contraction of 8% that affects the compression curve, compressibility, etc. And this is what I'm going to talk about. So we conducted square cell calculations on 64 atoms with different iron concentrations and calculate the enthalpy of high spin and low spin states versus pressure. And you can see a high enthalpy crossing at around 32 GPa here. That's the result we obtained in 2006, between 3 and 18% iron. It doesn't depend on the iron concentration within the accuracy of this calculation. The fact that it didn't depend on the iron concentration suggests to me that iron is not interacting with iron, because if they were, their spin state changes would somehow be correlated. So I interpreted this result as if we had a spin transition, a spin state change occurring in iron, irrespective of what is happening in neighboring irons. It's a local phenomenon, and high spin and low spin states exist in different irons independently, because these irons, in this low iron concentration, there is not much interaction between iron. So this is the static compression curve of high spin iron blue and low spin iron red, and this is the experimental data on 17% iron. The calculation had 18% iron, approximately 19. So what you can see here is you have the experimental data going from the high spin state to the low spin state in a broad pressure range from 45 to 65 GPa or 60 GPa essentially. This is what is a crossover. It's not a sharp transition. There is no symmetry change. and there is no discontinuity in the volume across this state change. It's a crossover. So, and you can see here, so based on my the interpretation of the compression curve, this compression curve, and the enthalpy crossing in different iron concentrations, I postulated that this crossover happened in a region where there was a mixed spin region, where some irons were in the high spin and some irons were in the low spin. So defining low spin fraction n as this one, the compression curve for n equal 1/3 and n equal 2/3, you can see here. There is the volume depends on the low spin fraction. And so then we need to do thermodynamics to understand this behavior, the behavior of the spin crossover at high pressures and temperatures. So given a certain, this phenomenon that I described to you, where irons are not interacting with each other, we defined, I decided to develop, we developed a model for an ideal solid solution of a high spin ferropericlase and low spin ferropericlase. This is not an ideal solid solution of MgO-FeO. The MgO-FeO solid solution, we take care of that because we do ab initio calculations in a supercell with iron and magnesium interacting with each other. This is a solid solution of high spin and low spin ferropericlase. Two solid solutions and N members with the same concentration, but with different spins. So the volume of an ideal solid solution is a weighted average of the volume of the N members of the high spin and low spin state. The free energy also weighted average of the free energy of the N members plus a mixing entropy that in the ideal solid solution has a simple analytical expression. The Gibbs free energy we calculate this way is the Helmholtz plus PV, and the Helmholtz is that given by the quasi-harmonic approximation, static plus vibrational. But it has an extra contribution coming from electrons. We call that electronic free energy, or comes from the electronic entropy or magnetic entropy. It's the magnetic contribution, the magnetic entropy. Magnetic because iron with S equal 2 has 2s plus 1 possible orientations of that ion in the atomic limit, which is the model we developed here. And so there are two analytical parts here, the magnetic entropy and the mixing entropy of the high spin and low spin states. All the rest is calculated by first principles. So putting these results together, minimizing the Gibbs free energy with respect to N, we develop a neat expression for the population of low spin states as a function of pressure and temperature. S equal 2 is the total spin of approximately the total spin of the high spin state. M is equal 3 is the degeneracy of the minority electron, 3 orbitals. And delta G is the difference in Gibbs free energy between a high spin and low spin state. We had to calculate in 2006 and 2008, we developed a vibrational model for the solid solution. Of that time, we couldn't calculate the vibrational density of states or the phonon dispersions of solid solutions because it was DFT plus U. We needed DFT plus U. So we developed a vibrational virtual crystal model where the cation, you can imagine what that means, cation mass is weighted average of the N members as well as the elastic force constants. The force constants between first neighbors were also averaged bet with the weighted average of those of the N members. So to make a long story short, there are a lot of anomalies caused by the spin crossover, and you are seeing here some of them. This is the thermal expansion coefficient, 0 GPa, 30 GPa in the high spin state. When you enter the mixed spin region at 50 GPa, you have a huge anomaly in the thermoexpansivity. But the really important anomaly is in the book modulus here. So this is 75 GPa, I believe. No, this is an properties of functional temperature at different pressures. And here at 50 GPa, you see a huge anomaly in the book modulus when it passes through the mixed spin region. Here is N of PT. This is essentially the crossover diagram. Blue high spin, red low spin. The rainbow is the mixed spin region, and the width of the rainbow increases with increasing temperature. The black line is the 50-50, 50% high spin, 50% low spin, and the white line is the same, but without effect of vibrations. The process is a measurement done in ferropericles with 25% iron. It's different. Of course, our transition pressure is smaller than most experiments, and this is a problem with the original calculation that was non-self-consistent U. And this is the experiment that I'm showing here. The rainbow measured in ferropericles 25% iron is slightly different. And we have investigated the origin of this difference as well. And I have some news. Also, in the fully self-consistent DFT plus U, the transition pressure is 70. It's not 45 or 50 plus 70, which is different. It's not as good either. So in order to reach some agreement with the experiment and to make predictions in the metal, we just shifted, have done a Dok shift of the high spin, low spin energy by 0.02 electron volts. But it's important to say here that the shape of the rainbow depends on the iron concentration, and I'm going to show you next. So this is the rainbow. These are the two experiments, lean with a vertical rainbow and a curved rainbow, and the rainbow determined by Komabayashi in 10% iron, lean 25%, Komabayashi 10% iron. So it's different rainbow shape. This is our rainbow shifted with the energy shift. If the slope of the rainbow depends very much on the magnetic entropy. Here we have that idealized analytical entropy, and this is when with zero entropy. It's plausible that higher iron concentration have interaction between iron, and one of the effects is to decrease the spin orientation degrees of freedom of the system and decrease the entropy and have a more vertical rainbow. Here on this side, we have a non-ideal solid solution where we really computed the excess free energy by calculating all possible configurations of high spin, low spin states in the supercell with 64 atoms and 18.75% iron. So the rainbow broadens considerably at all temperatures for non-ideal systems. And here, so you can see how the shape of the rainbow depends on models, on the features of the model. And this is painful to repeat these calculations using different approximations. But this is where we stand today. This is the understanding, okay? So we actually need to calculate elastic coefficients. I think I'm going to, between 2008 and 2011, there were 3 measurements that didn't agree with each other. Cubic system has 3 elastic coefficients, and these measurements with different techniques pointed to elastic anomalies in different elastic coefficients. So shear modulus, brilliant scattering said that there is no anomaly in the shear in the C44, the shear elastic coefficient. The others said it does. So we develop a formalism for elasticity across the spin transition. I don't have time to go through. Please ask me later if you do, if you want to know more. But it is based on an ideal solid solution, and we develop a formula for the compliance, with the components of the compliance tensor of the solid solution. And in this case, we showed that the shear elastic compliance component does not have an anomaly. In other words, the shear elastic coefficient does not have an anomaly. It's the longitudinal elastic coefficients that have anomaly. Also, this formalism, you needed to calculate the compliance tensor of the n members only, not of the solid solution. And that is the high spin and low spin ferropericlase, and we have been calculating thermoelastic tensors since 1999, and it's the elastic components of the elastic constant tensor are the second derivative of the Gibbs free energy with respect to strain. In the beginning, we did all this numerically, but now we do it in a semi-analytical way, which makes these calculations, these high throughput calculations, much more efficient. So we know how to calculate thermoelastic tensor of the n members. So here is what you see. This is 300 ambient conditions. These are the colored lines are our calculations of the Book shear modulus and the elastic coefficients of the solid solution with variable composition. And the symbols are experiments, and you can see there is good agreement. Here is our results for Book, adiabatic Book modulus and shear modulus as a function of pressure at 300 Kelvin. The experimental measurements on the adiabatic Book modulus coming from the elastic coefficients are here, and you can see the discrepancy between the data points, which are from experiments. Our calculations, the green line for 10% iron, agree quite well with Brillouin scattering, essentially, the Book and the shear modulus. And this is the effect of these anomalies on the on the acoustic velocities or compression acoustic velocities, longitudinal and shear velocities, and the Book velocity is just square root of the Book modulus divided by the density. So there are very large anomalies in this acoustic velocities. So, but this is ferropericlase, and it's in good agreement with the experiment. But here is the most important phase of the lower mantle, ferrous iron in bridgemanite and ferric iron in bridgemanite. It's very interesting, but I will have to cut this short. I'm going to show just a little about what's happening in ferrous iron in bridgemanite. Nope. Here. In 2008, most Bauer measurements in ferrous iron in bridgemanite indicated that there is a spin state change in ferrous iron. A low pressure, S equal to high spin state, quadrupole splitting 2.4 millimeters per second. Under pressure, a second kind of iron shows up with a quadrupole splitting 3.5 millimeters per second. Between 30 and 60 GPa, both kinds of iron coexist in the sample, and above 60 GPa, there is no more low quadrupole splitting iron, only high quadrupole splitting iron. It was suggested that this is the intermediate spin state because the quadrupole splitting increases, and we know that the low spin state has quadrupole splitting that's quite small. So we knew already to find different irons in different electronic configurations occupy different positions in the perovskite cage. So here we found two kinds of iron, high spin iron, with different quadrupole splitting sitting in slightly displaced positions in the A site of the perovskite structure, and one low spin iron. And the two kinds of iron are like this. One had a quadruple splitting 3.3 and the other 2.3, in good agreement with the experiment. And the low spin state have a quadruple splitting. It's pretty small. So this is what's happening with iron. You'll have a low pressure, the low quadruple splitting has the minority electron in the XZ orbital. And there is the other kind of iron with the high spin, with the minority electron entering in a different orbital. So there is a difference. There is a change in the electronic configuration of iron under pressure, where the minority electron jumps from one orbital to another, but this is not a change in spin state. So, and this is the structure of energy, the energy surface associated with these states as a function of pressure. So there is no spin state change in ferrous iron, in Bridgmanite, in the A site of the perovskite structure, and not ferric iron in the A site either. No spin state change in iron in the A site. Ferric iron in the B site has a spin state change like ferropericlase. It's iron sitting in the octahedral site. It happens that when you bring aluminum to the sample, then iron-rich aluminum bearing Bridgmanite, aluminum enters in the silicon site, and ferric iron has to be displaced to the A site, and there is no spin state change there. So therefore, we don't need to worry. The first approximation to study the pyrolytic lower mantle, which is the standard composition of the lower mantle, the most standard. We don't need to worry about spin transition in Bridgmanite. That's the most dangerous one. So this is the lower mantle. It's Bridgmanite with ferrous and ferric iron in the A site, aluminum in the B site, ferropericlase with up to 20% iron, and calcium white, highly anharmonic phase, which doesn't play much role in understanding, the effect of spin transition in the lower mantle. So here you have the elastic coefficients of ferropericlase at 75 GPa as a function of temperature. Suppose 75 GPa is 1500 kilometers in the mantle. And this is how the book modulus and shear modulus vary with temperature. The shear modulus decreases with temperature. In the absence of a spin crossover, the book modulus would also decrease with temperature. But because of the spin crossover, there is this anomaly here in the book modulus, and the anomaly increases with the iron content. So the GDT is negative at this pressure. The KDT at around 2000 Kelvin and beyond is positive. So there's an anticorrelation in these derivatives, and that will mess up with the signature of this a hot anomaly in the lower mantle, for example. So let me say a little bit more here. So here is the rock aggregate, the pyrolytic rock. We have 78% Bridgmanite, 7% calcium silicate, and 15% ferropericlase with different amounts of iron, just to investigate the effect. So here the GDT of the rock is negative and the KDT is still positive, and the magnitudes are not too different. So it happens that the compressive velocity becomes a little bit insensitive. If you're sitting at 1500 kilometers depth, 75 GPa, and there is a hot anomaly nearby, when you move to that region, the hot region, the shear modulus decreases and the book modulus increases. The shear velocity decreases and the compressive velocity become quite insensitive to lateral temperature variations. And this is the message here. If you have a plume coming from the core mantle boundary, in a tomographic S model, you will see a plume looking like this. But in a P-wave model, in a tomographic model, there is a disruption in velocity structure between 1500 to 2000 kilometers. That's because the book modulus increases with temperature and the shear modulus decreases. That's essentially the story, the prediction that we understood in 2014. But it happens that there were several tomographic P models of hotspot anomalies in the mantle and beneath hotspot volcanoes. And they look very interesting, and we could start seeing some correlation between our prediction and these images. For example, this is Hawaii, Iceland. These are plumes that we expect come approximately from the core mantle boundary. And you see the disruption in velocity structure in this P model exactly at the same depths that we predicted. Here, the same is the anomalies are slightly broader. Samoa, Canary, Cape Verde. And there is also this other study here of joint 2 global P models and 3 global S models. They looked at 40 hotspot anomalies or plumes in the common features in these models. So they analyzed 7 models, 5 models, 3S and 2P models. And what they concluded is that in tomographic S models, you can find up to 10 plumes beneath hotspots coming from the core mantle boundary. And this is this plot shows the vertical extent of these plumes for 40 hotspot volcanoes, beneath 40 hotspot volcanoes. But in P models, you couldn't identify a single continuous low velocity structure in the mantle, which is approximately what we would expect if this was related with spin transitions. So here is the anomaly, okay? The anomaly can exist also in cold subduction regions, okay? For example, this is a map of velocities, fast velocities, regions of fast velocities in the mantle, and you can see subducting plates, and this you can see is a disruption in velocity structures around the same depths. We embarked on a joint study of several S and several P models at the same time. It happens these models differ from each other. The heterogeneity, the amplitude of the velocity heterogeneity varies. The reference varies. So at each depth, you have a histogram of velocity distributions. And different models have different distributions centered at different points. So the first thing, what we really want is to extract the common robust features in these methods, in these models. And the first thing to do is to kind of normalize these histograms by aligning them, giving them the same average, and changing their width, normalizing their width. So we could pin down the degree of agreement of these models. And this is what is called a vote. We use these histograms and these normalized histograms to calculate vote maps, to build vote maps. And by asking the question, how many models at a certain point in the Earth, how many models have delta V larger than 1 sigma or smaller than minus 1 sigma? How many? So this is what a vote map looks like. This is a S wave map, and we have 4 models. So vote maps are not tomographic maps, but they just show the robust common features of the tomographic maps. Dark regions is where all 4 models agree the velocity is faster, is larger, the heterogeneity is larger than 1 sigma. And white regions is where the velocity heterogeneity is smaller than 1 sigma, or there is no agreement between the models. So, and here you see the tomographic, the volt maps for S-wave, fast regions and slow regions, Izanagi, Farallon, and African large low shear velocity province. And this is how they appear in P-wave models. They fade because the velocity heterogeneity is not large, or because there is no agreement between the models, most likely because the heterogeneity is really smaller, and that is really true. So in volt maps, this heterogeneities fade in the P-wave model, as we expect from a spin transition. And I leave you with this message here, with this model. This is not a volt map. This is a real tomographic map, and the latest is a waveform inversion. And these are the latest of these models. This is Farallon it's North Farallon actually, and this is the P-wave model. Actually, this is the bulk velocity model. This is S model, and this is a bulk velocity model, and you can see the plate Farallon disappearing beyond 1,500 kilometers in the bulk velocity model. So this correlates very well with our predictions. This is a single model, and a model that I put great faith on because there is no reference for calculation of these heterogeneities. This is full waveform inversion calculations of each velocity at each point in the Earth. So this is the effect of spin crossover in seismic tomography. It's indispensable for interpreting these maps in terms of mineralogy and temperature and understanding the Earth. So I thank my students, postdocs, and some more senior collaborators that helped me with this project. Thank you very much for your attention.